All right. Hello, everyone. Welcome to LLM System Seminar. Today it's my pleasure to have Jin-Kun Lin here to give us a guest lecture. Jin-Kun is now a postdoc researcher at Cornell. He graduated from NYU Systems Group, which just happens I also graduated from there. So, Jin-Kun is my younger academic brother, and Jin-Kun's work since PhD day one is about machine learning systems, with a focus on the correctness, robustness, and reliability side of ML systems. And his prior work, for example, in Smith, which is a tool to check the correctness of neural network compilers, has won the S+ Distinguished Artifact Award. And for today, he's gonna give us this, straggler studies in this large-scale training. With that, what's yours?
Thanks, Sean, for a nice introduction. So hello everyone. Today I'm very happy to come here to share our recent work about stragglers, and especially in this lecture format, which I think we have 1 hour. Yeah. So I guess we will have plenty of time to talk more about this work. And I also go at a lower pace and hope I can cover more details and answer all the questions you would have. As Sean said, feel free to interrupt at any point for any question. I feel you probably will have a lot of questions since you already have my favorite discussion in the previous lecture as I checked it a bit. So feel free to ask any of it. That's the start. So this work is about doing a study of stragglers in large model training using a methodology we call validation. And this is a joint effort between me, my advisors at NYU, and also for many folks from ByteDance LLM University. And it's been published at this year's OSPR. Let me start with the motivation. It's really why we want to do this work in the first place. I have to rewind the time back to 2023, which was a time when LLMs broke out shortly after the release of ChatGPT. And at that time, many companies in the industry started to train their own LLMs, which is a procedure we know called training. And ByteDance is no exception. They also wanted to train their models, and they do so by using the Megatron LLM framework from NVIDIA. But unfortunately, things never go as you expected. They encountered a lot of challenges, like failures, performance degradation, and also stragglers, which is our topic today. So they realized that stragglers actually happen quite frequently when they train a model, and somehow they feel they need many solutions to that. That's why we started this work. But before I talk more about this, I would like to make it clear by giving a definition of what I mean by a straggler here. But actually, this is also a question for you guys. Actually, I'd like to hear your thoughts, your first thoughts about the definition of stragglers as well. So what came to your mind before you read my paper? And when you first thought stragglers in LLM training, what is the specific scenario in your head? Anyone wants to share?
Yeah, I guess for me, it's going to be those type of either processes or machines that could have been turnaround time. That's my first impression.
Cool. I think that is perfectly exactly the definition I had in my head. I think the keyword here is slower than expected, actually. Also slow down the whole end-to-end training. So yeah, I'm seeing failures. Basically any unexpected worker that is lagging behind others at synchronization points. So let me give you a example, a graphical example here, which is a synchronous SGD algorithm implemented with data parallelism. Here, every process is one worker. You can think of it as one GPU, for example. And at the end of every training step, they need to synchronize the gradient before they can move on to the next step. And as you can see, the second process here runs much slower than others. That makes it a struggle in this training step. And as another example, which is pipeline parallelism, here shows two real timeline for BP. I assume you will have covered what pipeline parallel is, but I still remind you a little bit. So basically, pipeline parallel is a kind of parallelism. You partition a model into several stages, and you assign one stage to one GPU. And then you, when you want to do a computation, you do it in a pipeline fashion where every GPU will compute these training samples and then pass the intermediate result to the next GPU and all the way to the end. This is sort of forward pass. As illustrated here, what VPP is, because that is actually what is being used in practice in the industry. It's a kind of an improved version of pipeline parallelism, which is called virtual pipeline parallelism or interleaved pipeline parallelism. It's not quite important to understand the internal mechanism. But the thing that matters is now instead of just going one pass from the device, the first one to the last one, you kind of do it in two waves or by two loops. Now, the device forms a circle, and you go from first device to the last device. Then you go back immediately to the first device. And then you go to the end again. So basically, essentially, it's two loops of devices you have. And the same thing happens in the backward pass. You also do these two loops. And the dependency still matters here. You cannot start executing until the previous device finishes its computation. Okay, this is the ideal timeline you see in the. So this is actually two figures from Megatron LLM paper. However, this is the reality, which is this trace may seem a bit messy. I apologize for that. But I'll walk you through. So it's actually meant to be similar as the previous trace, where every line represents the computation or the timeline for every device. Now we have 8 devices as opposed to 4 in the previous case. And now the brown blocks represents forward pass, and the purple represents backward pass. And this is using a VPP schedule, the second diagram in the previous slide. And you may see some blocks. Okay, just be slow. It's not quite just basically, for example, you see these 3 blocks. They are kind of pushed to the second row. The reason is because of kind of a limitation, or you can also say it's a bug in our profiler. Basically, when we record the timestamps, we may actually introduce a small precision error, and that will make kind of a slight overlap between 2 consecutive operations. And turns out our visualizer doesn't like drawing 2 overlapping operations in the same line, so you will just push the second operation to the next line. But they should be all in the same line, and there shouldn't be any overlap. Okay. So now let's finally we can talk about the interesting part. So you see there's one block which is much longer than all other blocks. And this is one instance of the struggling operations. And this operation will cause delay of the previous device because of the dependency. Introduce a bubble where GPU just idles and wasting the compute power. And because of dependency, carries. So yeah. Let me talk a little bit about what our traces look like. We collected 5 months long training traces from ByteDance from their training clusters, which are dedicated for training LLMs. And this resulted in 3,079 retraining jobs collected, with the job sizes ranging from 128 to more than 5,000 GPUs. And these jobs use data pipeline, tensor, and context parallelism, and their combinations. And each job will have around 10% of the training steps being sampled, which is done by our in-house provider called Alikana. It's also open source, by the way. The result of the trace will contain time steps of a few coarse grade operations at every worker. I'll show you a graphical example. But actually, you have seen a real example in the beginning of the slide. But that's a bit messy, so I would like to show a inner version that I draw myself. So here shows a job trace using two-stage pipeline parallelism and 2 micro batches. The trace will record the start and end timestamps of the following operations, which are organized into different lines, as you can see here. And different lines represent different class streams. Here, the time flows from left to right. At the beginning, the first device in this pipeline will start the first micro batch. Starts its forward computation or forward pass. And then after it finishes, you will send the data to the next device using some communication operations, which is forward send, and the other device will receive the operation using forward receive. After which it will compute a forward pass, the second device. Then you can do the backward pass, and then similarly pass data backward. Then so on and so forth, continue the chain. Okay. So the operations here are recorded in the coarse granularity. Every computation is recorded at one entire pipeline stage instead of individual layers. So that's why you only see like so if this device has assigned 2 layers, they will be recorded as a whole. And for communication operations, they are recorded in this nickel kernel granularity. And if you further use data parallelism, say in a 0-1 style, which will add a parameter or getter at the beginning of every training step, and a reduce getter to accumulate all the gradients at the end of every training step. Okay. So to conduct this study, one important question is, once you see this kind of trace, how do you know if this job is suffering from stragglers, and how much does it suffer from stragglers? The first part of the question may be easier, the if part. If, say, someone gives you this trace, it probably will be very self-evident to say, okay, there's a straggler. But the part about performance impact will be less clear. Okay, let me continue. So our approach for this is using counterfactual reasoning. That's why we call it what-if analysis. So think about this. If there's no straggler in this job, what will you see in the trace you collected? Basically, we think all the operations, all the forward compute or forward pass operations should take the same time across all the devices. Same for all the backward compute operations. Same thing applies for essentially every operations of the same type, including communication operations. This is because in a straggler scenario, all the workers should progress in the same speed and finish all their tasks at the same time. So this may sound like a bit strong or like controversial even in the first place, but I think there's a fundamental reason for it. We didn't mention that in the paper because it may be a bit controversial, but I'll talk about it here and you can agree with it or not. So I think because a lot of the terrorism strategies used today are actually developed in this SPMD fashion. SPMD meaning single program, multiple data. It means that every device will run the same program, but just use different data. And in such a design or programming paradigm, is basically the simplest approach to make every device kind of homogeneous and compute everything, compute exactly the same thing, and basically execute the same sequence of operations and do communication at the same time. And in this kind of paradigm, to avoid any stragglers, you will essentially require every device to initiate its communication at the same point. So you should ideally assign every workload, assign the same workload to every device you have in the cluster. So one example is data pair. You do the forward and backward pass, and then you do the gradient synchronization. Ideally, you want to make sure every device finishes the forward backward pass at the same time, so that there's no struggle when you start the gradient communication.
Yeah, I slightly disagree. I think that's definitely true for tensor and also data parallelism. I think pipeline parallelism is the exception because what you're really doing, because if you think about if this is not transformer architecture where you just have different, back in the days in CV world, like you just have a very weird architecture, right? In that sense, it's not necessarily easy to partition like from the depths that I mentioned to be sort of equally, right? I think the benefit of today is that the transformer is pretty regular and this stack on top of each other, just repeat itself and you're done. So
yes.
I feel like that's not necessarily true, and also so that's
you may not generalize to other models. That's a question. For LLMs, because as you said, they use the same structure. So nowadays people do pipeline parallelism also in this SPMD paradigm because it's uniform. I think this kind of paradigm also makes the development much more efficient. So you can implement pipeline parallelism without considering a lot of imbalance, etc. That's also one reason that they get wide adopted. I mean, Megatron LLM, they use pipeline parallelism. I think in systems, being simple is usually is a good thing. Usually gets you good scalability.
Do you want me to cut this? That's fine. Okay, great.
Okay, so then we can define the slowdown here. First, we think when the job has no stragglers, it should achieve the lowest job completion time. And then we define the slowdown as the ratio between the original completion time to the ideal completion time. But how do we compute T ideal? This is the question I asked people. Like, how do you know? Basically, how do you know the slowdown? And we can also go back to this trace to have more to get more concrete. If I give you this trace, how do you know how much slowdown has the stragglers cost? For pipeline comparison, there's actually one corner case, which is also why we use a what-if analysis, because we try to be more fundamental. So as you can see, there are actually a lot of pipeline bubbles already. It's hard to distinguish between normal pipeline bubble and the other normal pipeline bubble created by stragglers. Yes, but fundamentally, we still follow the same direction. We try to remove all the bubbles. So what we do is we try to make this abnormally, so we don't actually directly operate on the bubbles. We operate on these operations that are abnormally long. Then we try to make it we try to cut it down to the same time length as normal. And then we kind of we simulate the whole trace, replay the whole trace with the new operating plan, so that we can know what will the trace look like. So just and yeah, things evident, self-evident that this block is. I mean, this one is much longer. It should be as short as maybe one of these. Right. So what we do is essentially making it short and then replay the trace. I will show you examples very shortly. Yeah, essentially we do these two steps. First is we will need to know what we consider as normal operation time for every type of operations. We call it an ideal duration, and then we replay the trace using the ideal durations. And let me give you one very simple example. You have this struggling trace where rank 1 is assigned double the workload compared to rank 0, making each a straggler. To determine the ideal duration, in this case, you should ideally distribute the workload evenly across all the devices. So let's just make the F as long as 1.5 seconds and B as 3. And then you resimulate the trace to get a straggler-free trace from which you can calculate the ideal time and then the slowdown. So yeah, to determine this ideal value, we actually use separate approaches for computation and communication respectively. Computation will do the same thing you just see earlier. We do the average because we think we assume that when you sum up all the operations time, it's the same as summing up all the workload, and you give you the total workload you have. And by dividing it up, by doing the average, it amounts to perfectly dividing all the workload across all your devices in a perfectly even way. But I think someone mentioned that it's assuming stragglers only is caused by workload imbalance. Yeah, that is kind of a limitation, or I should say, it's although it may have some small, it may introduce some small error in our estimation, but we think the error is not that big because of two reasons actually. First is most devices should be healthy, should be normal. So when you do this average, the large amount of healthy operations will kind of give you close to the true estimate anyway. The second is, as you can see in the later evaluation, indeed it is really because like mostly the stragglers are caused by imbalance instead of machine problems. And then the second part, communication. We now use average because, as what the other student mentioned, we will have a lot of unpredictability about communication, and that means basically you will see more jitters and even long tail distribution of the communication operations. So if you do average, average is not very robust to long tail distribution. So you will break, it will give you some not so accurate estimation. So that's why we switched to the median estimator. Still, we are making the assumption that most of the time your network should be stable, and the median estimation of the communication time should be kind of a good estimator of the true network time. So second step is to simulate using ideal theory. So this is also straightforward. That requires a little bit of engineering effort. First, we need to build this dependency graph between all these operations, and then we just do a topological sort to replay according to the dependency. And the dependency is inferred from a trace and also modeled manually according to our knowledge of the framework empirism strategies we use. To give you one example, this arrow points from sync prime to CF. Sync prime means the algorithm of the parameter in data pairism, and CF is the computation for the forward pass. And essentially, it means you cannot start the forward pass until you finish algorithm. So we started the following aspects of stragglers: how prevalent, how much impact they have, symptoms, and root causes. Let's look at the prevalence. Basically, we plot the slowdown of all the jobs in the severe graph, where x-axis shows the slowdown in log scale and in percentage. And if we define the job with slowdown greater than 10% as a struggling job, we actually see 42.5% of jobs struggle, which is actually quite a significant number. And the average slowdown is 1.15, but the tail could be much worse, more than 2x slowdown. So what is the reason behind all these strugglers? We identify the causes by the following. First, we will borrow from our past operation experience. Basically, we ask the developers what is the common root cause you have seen in the past. And then we also sample large jobs from our trace that have high slowdown and conduct some manual extraction. Okay, and that gives us a few root causes. I'll talk about a few of them. First root cause, worker problems. So this we studied this root cause because we want to understand how many straggler incidents were caused by machine problems, for which it only affect a few workers, a small number of workers. So that's why we call it worker problem. And to quantify how severe this root cause is, one important metric is how many jobs are affected. That means we need a classification algorithm to tell us whether this job is caused by worker problem or not. And the idea here is also straightforward. We know because worker problems should only affect a small number of workers. So if you fix these the few slowest workers, ideally you should recover most of the performance and matching the ideal performance we estimated. So that's what we do. We chose the slowest 3% workers to fix, and then we estimate what is the resulting performance you can get. But again, we cannot really go and fix the worker and rerun the job because that would be too costly. So we still use the same what-if analysis approach, basically simulation. So use a similar approach, but instead of fixing all the operations to ideal value, we only kind of idealize those operations on this set of workers. And to know how to know what this set of workers are, we develop a new metric called worker slowdown. This is also what I just mentioned to Cheng. This where the complexity of our algorithm comes from, which is also done by qualitative analysis. I will skip this part and check the detail in the paper. But once you have this, you can calculate for classification metric here, which is defined by this performance covered by fixing depth over performance covered by fixing everyone. And the ratio need to be large in this case. Great. Just time I will skip this example. This is just basically showing how we compute these two values and the MW. Directly jump to the result. The previous slide essentially says like worker problem should have a large MW, which is characterizing how much performance you can recover by fixing a small set of workers. And we plot MW of all the jobs, all the struggling jobs using CDF curve. And we choose a relatively large threshold, 50%. We see that actually not many jobs can cross that threshold. Means that worker problems are not a common cause. But we also check these jobs. We find that it actually causes higher slowdown. They introduce like 3.04 slowdown on average, much higher than the average for all the struggling jobs in our traces. The implication is, yes, we still need the traditional health metrics to monitor the machine problems, but they are not efficient and they are not sufficient to help avoid most struggles. So what are the common causes that we found? This is one of them, stage partition imbalance, which refers to the case where the last pipeline stage is much slower than all the previous stage. The reason is because there's one, there's kind of some asymmetry, right? In the large language models, in the last pipeline stage, you will have one loss layer, which is different from transformer layers. And when you have large vocabulary size, it could be much longer to run compared to transformer layers. That means it's actually hard to partition evenly when you have large vocabulary size. It also requires careful tuning on job by job basis, which was not done at the time we collected the trace. So that's why we see a lot of root causes because of pipeline imbalance. But to quantify the stability, we again use a similar metric, qualitative metric as before. But instead of fixing the workers that are the slowest 3%, we fix a worker in the last pipeline stage because we know like they are the problem. And again, we plot the result in CDF graph. And now we see a difference. The 50% threshold actually lies in kind of a middle point in this curve. It means that, yeah, it's a common root cause. We have around 40% of jobs can be classified to this root cause. And we also find that even with tuning on job by job basis, so you can tune to the best case, it's still insufficient to get you the best performance, the ideal performance. The first reason is because the tuning is actually in a slightly cost granularity. You can only adjust at one transformer layer at a time. So in one of the case studies we conducted, we find we still have 5% performance left for a table compared to the ideal case. In addition, this tuning cannot address a limiting scalability issue because imagine when your vocabulary size continues growing, you will have a longer loss layer. And that means you have to use a larger pipeline stage to accommodate this loss layer. And that means you only be able to partition into fewer stages, which is the number of the PV degree you can scale along the pipeline direction. So I think the implications here are, first, you need to have auto tuning so that we can at least get some performance improvement. Second, we also need to consider slicing the loss layer across different devices when the vocabulary set becomes larger. So there are more root causes. Two other common ones are sequences imbalance and Python's garbage collection. So now I can finally answer the question I raised at the beginning. So what is going on in the first trace I show you? It's because of Python's garbage collection. And this garbage collection will stop the work of the Python execution, meaning that you will not be able to execute any Python code. And because in Megatron LLM, it is written in Python, and it launches kernel in the Python side. So once you are doing GC, you are not able to launch new kernels. That's why you will see GPU be blocked by the host by the Python side. There are some common cases, but also interesting, like GPU memory fragmentation, post-kernel dependency. You can find the details in the paper. So do we still have time to? Yeah, I think you can do 5 minutes. Okay. That'll be quick. So I only have two slides left. And this part, I'm going to talk about how we deploy our approach to help ByteDance fix a straggler problem in production. So the previous analysis was done offline. Of course, we want to see if we can continuously do this analysis online and help them identify stragglers. So that's why part of the analysis was deployed into a system called SMO and has provided two benefits to the developers and to the operation in ByteDance. First is it serves as a real-time straggler monitoring service, which can automatically analyze every new trace you collected, and then produce an analysis report that contains many useful metrics like the estimation of slowdown that we introduced in previous slides. Using this report, you can configure various other triggers. For example, they have configured to alert when they see a large slowdown or when they see a pattern indicating machine problems so that they can go and fix the problematic hardware. Second benefit is so SMO also facilitates manual troubleshooting when you find a particular struggling job, you want to understand why. This is enabled with a heat map representation where we organize all the workers in this two-dimensional grid. On the x-axis is PP ranks, y-axis is the PP rank. And every cell there's one worker in this intersection. The color represents how slow this worker is, and can help us locate the slow workers in a very straightforward way. For example, in this case, it is the stage partitioning imbalance that we talked about earlier, which is because of the workers in the last stage being slower. So as you can see here, the last row corresponding to the last pipeline rank will be highlighted here. Yep. So that's how you can identify this slow workers very easily. It can also help you identify the root causes by looking at a pattern. So here, I showed three different root causes. The second is because of worker problem, which, as I said, only affects a small number of workers. So that's why you see only one cell getting highlighted. And the third graph is sequences imbalance. This is the root cause that uniformly affects all the workers because of, I think one student mentioned this earlier, because of the imbalance of data distribution. So some workers get more data at some point, but this is purely random. So that's why you see every worker gets affected and being highlighted. Yeah, so that's all for the finding and the technique. So in conclusion, in this work, we present a comprehensive comparative study of stragglers production traces using motif analysis. In which we study straggler impact, symptoms, and root causes. And we also show that SMOND has helped developers and operation teams to monitor and diagnose stragglers in production. And yeah, that's all of my talk. Thank you.